So which one do we have a question over first? 7 and 8. So 7 and 8.
I was trying to figure it out, but I couldn't. Like, I watched the video and went over it again.
So we'll look at 7. 7 and 8 are actually the same. But I think once you see 7, 8's going to make a lot more sense. So we have 8 to the 4th over 10 to the 4th, all to the negative 1/4. Now, one way we can look at this is pull that factor of 4 back out, because since 8 and 10 are both to the 4th power, we can pull that power out, giving us 8 over 10 to the 4th to the negative 1/4. And part of the reason we do this is, 1, 8 over 10 is going to reduce to 4 over 5. Now, powers of powers multiply, yes? So 4 times negative 1/4 is what we're looking at. Well, 4 times negative 1/4 is, well, negative 1. Now, this is going to be more of a side note, because a over b to the negative 1, if we applied it to both terms, it'd be a to the negative 1 over b to the negative 1. Well, to make those exponent positive, we've moved from b from the top of the fraction to the bottom. Yep. Or we could have said that a over b to the negative 1 is the same as b over a, which for us would be the force. And number 8 is the exact same thing. If you notice that one, instead of force, 4 and negative 1/4, I think it's 3 and negative 1/3. So it's really going to be treated the exact same. Any other questions on the homework? Questions? No? You're good? Okay. Now what? Yes. Yes.
I got x equals 5 plus or minus 4 and
Yeah. Yeah, so 5 plus or minus 4. If we can add and subtract, we need to add and subtract. So that is the 5, 1, 2. So we get to x equals 5 plus or minus 4. So five plus 4 and 5 minus 4. Well, we can add 5 and 4 and get 9, and do 5 minus 4 and get 1. If we can add and subtract, we need to add and subtract. Now, if they told us that it would say 5 plus or minus the cubed root of 4, we leave it there, because we can't take the cubed root of 4 without turning it into a decimal. Any other questions? Yeah, because if we can add or subtract, we need to add or subtract. Yep. 9 2/3. Of course. Look right. Thank you. All right. Again, just like Thursday. All right, guys. Just like Thursday, we're going to be simplifying radicals. Now, simplest form, you can I didn't put these back on the sheet because, again, we had them on 5 2 1. Simplest form. No radicands have perfect nth powers. We can't leave something as, say, the square root of 8. Because square root of 8 is the same as square root of 4 times 2. Well, square root of 4 is 2. We're left with 2. If we can reduce it, if there's a perfect nth power inside the radical, we have to reduce it out. If it can be simplified, we need to simplify it. Essentially, a fraction form of this first one is saying that the answer is 8 halves. We don't leave something as 8 halves. We just say it's 4. If it can reduce, we need to reduce it. Second one, no radicals or radicands can contain fractions. We can't leave something as a square root of 2/5. We can't have a fraction inside the radical. And the last one is we cannot have a radical in the bottom of a fraction. And again, we had these on Friday. I'm reiterating, these are simplified forms. Now, properties of radicals. Product property says if I have the nth root of two things being multiplied together inside the radical, we can write it as two separate radicals. So that can be helpful, especially like, say, the cubed root of 8, or if two of the terms can be reduced, we can split them up, or we can put them together and then reduce them. Quotient property, if we have something being divided inside the radical, we can break it up into two separate radicals, or we can go the other direction. Now, using these properties of radicals to simplify expression is what we're going to do. Now, the first few that we're going to look at, really the cubed root of 12 times the cubed root of 18. This one here, the graph, or the 30xs will simplify. Graphing would simplify. Unfortunately, once we go past square roots, the 30xs, our yellow calculators, will not leave it in radical form. It'll do it for square roots, but anything above it, if it doesn't reduce nicely, it's going to give it to us as a decimal. We need it in radicals. Now, for cubed roots, we're looking for a number times itself 3 times. So 3 groups of 2, or 3 groups of 3, or 3 groups of 5 that we can take the square or cubed root of. Now, one of the main ways that we can do this is factor trees, because cubed root of 12, there's not a number that we know of that will multiply by itself 3 times. And if we look at the factor trees, well, that'd be, say, 2 times 6, and 6 is 2 times 3. Telling us that the prime factorization, or the broken down version of 12, is 2 squared times 3. So that kind of tells us why we can't take the cubed root, because there's not a factor of 12 that is a number times itself 3 times. So we could rewrite the cubed root of 12 as the cubed root of 2 squared times 3. Now we can do the same thing with the cubed root of 18. So again, we'll look at the prime factorization of 18 using our factor tree. Smallest prime number that goes into 18, 2 times 9. And well, 9 is 3 times 3. So 18 is 2 times 3 squared. So with 18, we can't take the cubed root of 2, or we can't take the cubed root of 3 squared. We don't have enough. We would need at least 3. No. Because that's the nice thing about multiplication. We can multiply any group of things in any order. Okay. Questions on what we've done so far? Really, we've just factored this thing down. According to our product property, if I have 2 radicals with the same index being multiplied together, we can make it a single one with what's inside being multiplied. So we have 2 squared times 3 being multiplied with 2 times 3 squared. When we multiply like bases, we add the exponents. So our 2 squared times 2 would be 2 cubed. Our 3 times 3 squared would be 3 cubed. Now I can take the cubed root of 2 cubed, and I can take the cubed root of 3 cubed, because we have enough to take the cubed root. We kind of see how that works. Yeah. It ends up being in and of themselves. I can't take the cubed root of 12. I can't take the cubed root of 18. But the cubed root of 12 times the cubed root of 18, I can take the cubed root of it. Now, we don't have to do this, but I'm going to go on and do this step. Just like we put them together, I can pull them back apart. Because it's the same as saying the cubed root of 2 cubed times the cubed root of 3 cubed. Well, the cubed root of 2 cubed is 2. The cubed root of 3 cubed is 3, and 2 times 3 is 6. Really, if we can see that we can take the cubed root of 2 and the cubed root of 3 here and go straight to 6, yes. 2 times 3 is 6. That's really all we're saying. Questions on this here? Because really this is factoring it down and taking out our groups of 3 in this case, or whatever our nth root is. Questions on A? Any other questions on A? We already looked at B. Now the issue with B is we cannot have a radical in the bottom of this fraction. So we can't have the 4th root of 5 in the bottom. Well, can't take the 4th root of 5 because 5's prime. There's not a number of times itself 4 times that gives us 5. The other option is if it works out, the number on, because we have the 4th root on top, 4th root on bottom, is 80 divisible by 5. Yeah. So what we could say, according to our quotient property, is that this is the same as the 4th root of 80 divided by 5. Well, 80 does divide by 5 nicely, and it is. It's not 32. 16. Do we have a radical on bottom of the fraction? No, there is no bottom of the fraction anymore. It's simplified out. We got rid of the fraction radical in the bottom of the fraction. I actually got rid of the fraction in the radical. We just had the 4th root of 16. So now it's seeing if we can take the 4th root of 16. If it simplifies nicely, the calculator would do it. The other way is just looking at the factor tree for 16. Well, that's 2 times 8. 8's 2 times 4, and 4 is 2 times 2. So 16 is indeed 2 to the 4th power. So what would the 4th root of 16 be? Yes? 2. And luckily enough, if they do simplify nicely, either calculator would do it. The 30xs would take the 4th root of 80 divided by the 4th root of 5. Clear on that now. 4th root of 80 divided by the 4th root of 5, telling us is indeed 2. All right. Let's look at these next two. The cubed root of 4 times cubed root of 128. Unfortunately, we can't take the cubed root of 4. Well, 4 is 2 squared. I think we're comfortable saying that and not doing the factor tree to show that 4 is indeed 2 times 2. We feel comfortable there. 128 is 2 times 64. And 64 is 2 times 32. 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. Telling us that 128 is 2 to the 7th power. So could we take the cubed root of 128? Yeah, it wouldn't simplify out completely, but we could take some of the factors of 2 out. Because again, for us to simplify that cubed root, we're looking for groups of 3. Well, we have 7. 2's. So we could actually pull out more than one group of 3. How many could we actually pull out? 2, 3, 6. Could simplify out. Because we could simplify it out there, or we could multiply and then simplify also. Because when we multiply these here, since they both are cubed roots, we have 2 to the second times 2 to the 7th. When we multiply like bases, we add the exponents, telling us that we're taking 2 to the 9th. Well, how many groups of 3 2's are in 2 to the 9th? 3. So that would be the same as 2 cubed, and we can go from there. Now, I did this last hour. I'll do it again this hour. There are different ways for us to get there. Product, power of a product, because when we multiply like bases, we add the exponents, yes? So we can say, to get this here, especially with 3's, well, it's the same as 2 to the 3rd times 2 to the 3rd times 2 to the 3rd. Cube root of 2 to the 3rd. Well, that would just be 2 times 2 times 2, which is 8, because our cube root and third power would cancel. Does that kind of make sense how we get there? Okay. Now, let's go. Powers of powers. Powers of powers multiply. So 2 to the 3rd is the same as 2 to the 9th. Well, our cubed root and that outer third power would cancel, telling us that we're left with 2 to the 3rd, which is 8. Now again, you do not have to solve at every single one of these here. I'm showing you these here because, again, there's more than one way to simplify it down once we get to this radical form. Now the last way we had, and I've written before, the nth root of a to the x is the same as a to the x over n. Now this last way works out nicely if that rational exponent is simplified nicely. N in our case is 3 and x is 9. So the cubed root of 2 to the 9th is the same as 2 to the 9/3. Well, 9 divided by 3 is what? 3. 2 to the 3rd is 8. So it's really all about how we're simplifying these perfect nth powers with the root. But again, you don't have to do all 3. If one of these 3 or one of the ways makes more sense than the others, do it. You don't have to do all 3. Because we all 3 of these get to the same place. Because even with the rational exponent, our whole numbers, how many divide out evenly, go outside. The ones that aren't are even go inside. Because one of these 3 at least makes sense once we get to the bottom. Yeah. But it's just multiple ways to use those properties of exponents and radicals. All right. Fifth root of 192 divided by the fifth root of 6 is 192 divisible by 6. Yeah. 32. 192 over 6, which is indeed the fifth root of. Yes. All right, guys. Let's focus in. Because 32 would be 2 times 16, 2 times 8, 8 is 2 times 4. Yeah. Because 32 is 2 to the 5th. So 5th root of 2 to the 5th is 2. 5th root of 32 is 2. Because if they divide nice and we get these nice powers, it works out great. Because really all 4 of the ones we've done so far, we could have stuck it in the calculator, the 30xs, or graphing, either one, as it was, and it would give us an answer because it simplifies nicely. We ready for the next one? Well, if that's the case, cube root of 135, might as well just type in the cube root of 135. Okay, this one doesn't simplify nicely. But if we do the same method we've been doing, I take 135 and do the factor tree. Well, 2 is not going to be a factor because it's not an even number. 5. I would pick the first prime number that we see, which is going to be 5 times 27. 27 hits 3 and 9 and 9 is 3 and. So our prime factorization would be 3 cubed times 5. The graphing calculator is going to force decimal pretty much every single time. There are methods for getting it to do cubed roots, but every single method I've seen is either one, programming the calculator to do it and running a program through it, which takes a good bit of time to program and then interpret, and the other involves graphing, which is possible, but I feel it's going to take you more time to do it that way than it is to just do the factor tree. All right. Cubed root of 3 cubed would be what? Because we could split it up as the cubed root of 3 to the 3rd times the cubed root of 5. Well, the cubed root of 3 to the 3rd is indeed 3. Cubed root of 5 is the cubed root of 5. Because the reason we could simplify the cubed root of 3 is, well, there's 3 3s. The cubed root and that third power would cancel. I only have 1 5. It will not simplify with that cubed root, telling us that this is 3 times cubed root of 5, or 3 cubed roots of 5. This is why the graph or the calculator gave us that decimal approximation, because it won't simplify any root with an index greater than 2 in radical form. But that's it. Questions on this here? All right. Let's look at the cube root of 500 before we look at the other one, because I want to do another one of this type and then go hit 2 of the other. Cube root of 500. All right. Let's do a factor tree. So 100 times what? So 5 times 100. 100. Well, we can do 10. We can do, well, yeah, we can do 10 times 10. Well, 10 is what? 2 and 5, 2 and 5. So we have 2 twice, and we have 5 how many times? 3 times. So it's the same as 2 squared times 5 to the 3rd, which is kind of nice because that does tell us we can take the cube root of 5. Because we have the cube root of 2 squared times 5 to the 3rd. Well, can we take the cube root of 2 squared? No, we don't have enough 2's. Can I take the cubed root of 5 to the 3rd? Yeah. Now, I wouldn't leave it as 5 cubed roots of 2 squared, because what is 2 squared? So it's 5 cubed roots of 4. Questions on doing these here? Essentially, it's the same as what we just did, but we get it in that factored form, and pull out as many groups as that nth root as we can, and any are left over are left inside the radical. All right, we're ready to go back and do our division one. Fifth root of 7 divided by the fifth root of 8. Well, it'd be very nice if 7 divided by 8 nicely. It's not going to. Now, if we look at our factor trees and factor this out, well, the numerator is going to be the fifth root of 7 because 7's prime. There's no way to rewrite it. 8 could be 2 to the third because 8 is 2 times 4. 4 is 2 times 2. Gets us there. Now, what would be nice is if we could somehow, normally it's going to be multiplication, multiply the denominator of this and get 2 to the, or the fifth root of 2 to the fifth, or the fifth root of 2 to a power that is a multiple of 5. So 2 to the 5th, 2 to the 10th, 2 to the 15th. Something where I can get those groups of 5 2's out. Something that's going to reduce that radical. Well, the first number, power, after 3 is going to be, well, 5. We don't want to go above that because it's just adding. Because if I had 5 2's in the bottom, fifth root of 2 to the 5th, well, that would just reduce to what? 2, yes? If we could do that, that'd make things nice. But we can't. Because we can multiply this bottom of the fraction by the fifth root of 2 with what? How many 2's am I missing? 2, so I can multiply the bottom of it by the fifth root of 2 squared. We're also going to multiply the top by the fifth root of 2 squared. And there's a specific reason we can do this. What is the fifth root of 2 squared divided by the fifth root of 2 squared? 1. So really, what are we multiplying this fraction by? 1. We're just multiplying it by what I call it a fancy version of 1. We're not changing the value, we're just changing how it looks. So when we do this, fifth root of 2 to the third times the fifth root of 2 squared is indeed the fifth root of 2 to the fifth. On top, well, we're going to have the fifth root of 7 times 2 squared. 7's prime. But we can't take the fifth root of it. We can't take the fifth root of 2 squared. Since it is prime, there are no like terms, like in the first one where we had that 2's and 3's they gave us. Perfect fifth roots, or cubed roots. So all we have to do is just, well, to finish this up, we just multiply that out. 7 times 2 squared is 28. Really, 2 squared is 4. 7 times 4, 28. The calculator can do 7 times 2 squared for us if we need it to. So that's as simplified as it gets. So really with these here, when the fraction doesn't divide, we're trying to see how many more terms or factors in the bottom of that fraction do we need to get it to simplify. Well, I think we're all comfortable in saying that 4 is 2 squared. So we have the fourth root of 19 over the fourth root of 2 squared. So we need to multiply the top and bottom of this by a fourth root so that the denominator, in this case 2, fourth root of 2, has an exponent that is a multiple of 4. Now, it seems odd that I'm saying multiple of 4, not just 4. And the reason I say that is, well, if, not this one, but if we had, say, we simplified the denominator and found out we have the 4th root of 2 to the 5th. 4 is not going to be our next exponent because we've already gone past 4. We have an exponent of 5. So to get that radical to reduce, we would need a next multiple of 4, which would be what? After 5, it would be 8, because we can take the 4th root of 2 to the 8th. Or, if it was bigger than 8, we can take the 4th root of 2 to the 12th, or to the 16th. Yeah, I put it there just as an example. Yeah, because if it doesn't work for this here, but 2 to the 5th, well, I can't just say it'd be 4. It'd have to be 8. Because that would be the next one that would reduce. But here, it is indeed 2. But if it was bigger than 4, our index, we'd have to go to the next 4, or the next index after it. But here, we just need it to be 2 squared. We have 2 2's. We need 2 more to give us that, what? 4th root of 2 to the 4th. Well, the 4th root of 2 to the 4th is 2. And even if we had more than one term, we would do the exact same thing and just get both of those terms in the bottom of the fraction to that index. It would be 4 or 5 or 6. We need to get those to match up or be a multiple. In the numerator, we have the 4th root of 19 times 2 squared. And again, as I said before, well, 19 is prime, so here, 2 squared would be 4th root of 76. Then reduce. Questions on these here? Are you ready for the next one? So, last thing we're talking about today is this. 1 over 5 plus the square root of 3. So, for us to have this in simplest form, we cannot have a radical in the bottom of the fraction. So for this here, we're going to multiply the top and bottom of this by the complex, or not complex, but the irrational conjugate. Just like our complex conjugates, we take whatever the term is and switch the sign in the middle. I throw a marker. Because the whole goal of doing this here and multiplying it by this 5 minus the square root of 3 over 5 minus the square root of 3 is to get the radicals out of the bottom of this fraction. Now we'll look specifically at the multiplication of the bottom, then we'll do the product of top on next. Well, this here, 5 times 5 is 25. 5 times negative square root of 3 is negative 5 square root of 3. Square root of 3 times 5 is going to be positive 5 square root of 3. And square root of 3 times negative square root of 3 would be negative square root of 9. So far we've multiplied our 5 plus the square root of 3 by 5 minus the square root of 3. Now one of the nice things with this product is, well, 25 at this point doesn't have any like terms. Negative 5 square root of 3 plus 5 square root of 3 is 0. Minus, well, square root of 9 is 3. So multiplying by this irrational conjugate got the denominator to become 22. It removed all radicals from it. So that's just doing the denominator multiplying by the denominator. We also have to do the numerator. Okay, are you ready for this? 1 times 5. 1 times negative square root of 3. Or if we want to, we could say this is also negative square root of 3 plus 5 over 22. Same answer. Yes. Yeah. But again, the reason I show you this here is so that you know how to do it, how we actually do the simplification. Square roots are nice. Questions on this here? (14, 15, 18, 20, 22 through 28 even, 31 through 34. Really, I could have just said, what, 18 through 28 even? Yeah. That's it.